which giant components exists, we can do this calculation. Okay, so we can calculate the average. So if I randomly draw a node, calculate the expected component size this node belongs to. But that is not, so as I said, the component size, i's component size is 1 plus the sum of i's friends' component size, excluding the original link we found with friends. Okay, but this is not self-generating because the number of the size of a component i's friend belongs to, excluding the original link, this is a different random variable from the number of friends I has, sorry, not friends, from the component size, the size of component I belongs to, because we find I by randomly picking a node, we find J by randomly following a link. So to be able, what we need is to find a self-generating relationship. And we can actually. So we get J by randomly picking following a link. Okay. And so now we can calculate that's I call S tilde. S tilde is the size of a component J belongs to, exclude, and we find J by randomly following a link. And then we kill that link and ask what's the remaining component, the size of the remaining components J belongs to. Okay, so let's call that random variable S tilde. But S tilde, we do that, we can find J's friend. J's friend, let's call it K1, K2, K3. So we find J's friends also by randomly following a link. So then J, we find J by randomly following a link. We find J's friends also by following a link. So then J, let's say S tilde is a component J belongs to, the remaining component J belongs to. After excluding the link, we find J, the link that helps us, that gets us to J. We can do the same we can ask what's the size? The size of component, K1 the size of the remaining component K1 belongs to. After killing the link, we find K1 by. Same thing with K2 and K3. So then the idea is S tilde is roughly 1 plus the number of friends J has, excluding the original link. So that will be J's friends, D tilde minus 1 times S tilde. So it's not exactly true because each one is random variable. But when we're averaging, then it doesn't matter. So this is how. So phi is not. So definition of phi is wrong here. Phi is we randomly follow. So it's the size of the remaining component. The size of the remaining component after randomly following and killing a link. Okay, so phi is the expected number, the expected component size that J belongs to after killing this link. So what is that? It's 1 plus, well, we're taking expectation over the number of friends J has. But since we're killing a link, so say if J has D friends, now after killing the original link, J only has D minus 1 friends left. So that's a D minus 1. So, but then what's the distribution of the number of friends J has? So P tilde D is the probability that J would have D friends. Because we find J by randomly following the link. And then so if, for average not S tilde. The random variable is S tilde, the average is phi. So this is what we have. Okay? So we sum over all possible numbers of D, find the number of D, and then with probability P tilde D, J has D friends, and then excluding the original link for each of the remaining D minus 1 friends, that friend, the size of the remaining component is phi on average. Okay, so then you can get this is what phi is. So if phi is finite, then that means the component size on average the component size J belongs to is finite. Then giant component doesn't exist. But if phi is, there's no solution to this, so phi would be infinity because, well, if phi is infinity, then the equality can solve the equality. Okay, so giant component exists if and only if there's no finite solution to this equation. And so what you have is giant component exists if and only if the expected value of the square of the random variable, that is the degree of the node, is greater than 2 times the expected degree. So for Poisson random network, what that means is that, well, a giant component exists if and only if the expected degree is greater than 1. Okay, so, well, this is kind of intuitive that if on average you can find more than one friend, then the component size, I mean, doing it this way is going to give you infinite number of people. Okay, so that's, yeah, the threshold for existence of giant component. And then what we do, so what, when price, if valuation is independent of number of friends, then whether someone is probability, a node is acceptable is just 1 minus p. Then what we're going to get is, it's something very similar to this. So what you need is, for Poisson random network, a giant component exists if and only if the expected number of friends is greater than 1. So you can kind of see if price is higher, the probability a node is acceptable is going to be smaller. So you're killing more, given some random network, you're killing more links. So if you're killing more links, you're killing more nodes, then the expected number of friends is going to be smaller. So intuitively, if price is higher, it's less likely that giant component would exist. And the result you can kind of expect is that there's a critical price, such that if price is below this level, then a giant component exists. Otherwise, a giant component doesn't. And so that means if price is above the critical price, in the limit, no one will know about. Like, it won't spread. So no one will know about the product, almost. Okay, but still we need to know, because knowing that a giant, because of course the monopolist, if his marginal cost is not too high, he's going to price below the critical price. But then the question is, how would his price affect the fraction of consumers who will buy it in the end? And that will be the fraction of people in the giant component. So we can't just be satisfied with knowing when a giant component exists. We need to be able to calculate the fraction of people in a giant component. Okay, so we need to do a little more. Okay, so we need to use the probability generating function, that technique, to be able to find the fraction of people in the giant component. Alright. And then we we also need to just incorporate susceptibility. Alright, so now what we want is let's find what we care about is component size of a randomly picked consumer in the word of mouth network. So let's randomly pick a consumer. The probability that she is susceptible and has D friends is PD, the probability that she has D friends, times QD of P. That is probability that she is susceptible conditional on having D friends, given the monopoly price P. Okay, so the probability generating function of this distribution is just we substitute PD with PD QD, okay, because we need to take into account whether this person is susceptible or not. So what this is doing is, let's say if we randomly pick a person and inform this person. Now, including this person, how many consumers will become informed? So let's say, let me repeat. Let's say somehow we randomly pick a consumer and inform this consumer of the product. So this consumer is randomly chosen as a C. Now, including this consumer, what's the number of consumers that will be informed? So if this consumer is not susceptible, then he will not share. So the number will just be 1. But we can just count that as 0. If this consumer is susceptible, now she will spread to all her friends. All right. She will spread to all her friends, and then we can then ask again. So for each of her friends, so now each of her friends will become informed, and then we can ask the same thing now. But the difference is that we find her friends through randomly following a link, but then each of her friends will become informed, and then we can ask now what's the number of people that each of her friends, after being informed, will inform. So that's how many people will this friend inform? Okay. So we have F0 is the number of so after seeding a consumer, randomly seeding a consumer, what's the number of, or randomly informing a consumer, what's the number of consumers that will become informed? Okay, so now we're not asking about component size, we're just asking about the number of friends. Okay. So just notice that if we put x, we sub x is equal to 1, then here we're just summing up. It's PD. I have to write down what this F0 of 1 given price P is so now, so we have f0 is a probability generating function of the number of consumers that will become informed after you randomly inform a consumer. Okay. Now we can do the same thing. Now it's if you randomly follow a link, so you randomly pick a link and then inform one of the ends, one of the consumers. Right. Now you ask, what's the number of consumers that will become informed? So again, if this person is susceptible, then this person will inform all her friends. So then you're just asking, then in that case it will be 1 plus the number of this person's friends. But now you find this person by following a link instead of just picking a node. Okay, so yeah, so probability that when you randomly follow a link, this consumer is susceptible and has D additional friends, excluding the original link, is this one. So for him to have D additional friends, he needs to have D plus 1 links initially. Okay, and then we find the probability generating function of this random variable. Okay, so let's call F1. So F1 is related to F0 by, so it's, yeah, F0 prime divided by expected degree. So this is similar. So when we do, this is related to, it's really just the same. Okay. The two G functions. Except that here, there's no question about susceptibility. We're just asking, we're talking about the friendship network. And here, we need to ask if this person is susceptible or not. Okay. Now we want to do a component size distribution. We're doing really the same thing. So we randomly pick a consumer in a friendship network, and then we want to ask, so let's S be the size of a component in the word of mouth network it belongs to. So of course, if she herself is not susceptible, the word of mouth network she belongs to has size 0. And if she is susceptible but has no friends who are susceptible, then this component has size 1. Okay, but anyway, so S is the size of a component in the word of mouth network that a randomly picked consumer in the friendship network belongs to. So we denote the probability generating function of this random variable by H0. So this is, S is a component, the size of component that I belongs to. But in the word of mouth network, not just a friendship network. Now J is I's friend. So we need to know the number of, so the size of a remaining component J belongs to. So what we do is, so we find J by randomly following a link in the friendship network. And S delta is the size of a component in the word of mouth network, excluding the original link this consumer belongs to. And then we denote this probability generating function by H1. Okay, so I'm going to use something about probability generating function. So if you have two random variables, x and y, gx and gy are their probability generating functions respectively, then probability generating function of the random variable x plus y is just a multiplication of the two probability generating functions. And if you want to generate a probability generating function of the random variable x plus 1, then it's just So here I use z instead of x. Just you multiply, so if it's power generating function of x is gx of z, then you just multiply that by z. Okay. Now we're going to calculate, so h1, this probability generating function plays a similar role with phi. So phi was the average, the average number of remaining component size, the average remaining component size of that a consumer is really, you have to say it, I don't find a very good way to express this thing. It's, you randomly follow a link. So a consumer, you find a consumer by randomly following a link. You ask the size of the remaining component this consumer belongs to. After killing the original link, you find this consumer by. So phi is the expected value of this random variable. h1 of x is the probability generating function of this random variable. Okay? So earlier we find phi by an equation because you can express phi, you can do self-generation for phi. The same thing holds here. It's just that we're, instead of just calculating the average, now we're doing the probability generating function. And notice that, so phi is the expected value of this random variable. h1x is the probability generating function of this random variable. So phi is just expected, yeah, h1, fine. So it's expected value, so you take first order derivative. Okay. So now let me do two things. So let me just start with this one, since we're going to do the same self-generation. Okay, so we're going to use this expression. So S delta is the size of remaining components that J belongs to, excluding this link. What is that? That's 1. That's J plus D delta minus 1. D delta is the number of friends J has, minus 1 because it's excluding this link. So then what we do is, for each of J's remaining friend, we add up their remaining component size. Okay, so now, what's up? h1x, the probability generating function of this random variable S delta. It's, well, first, S delta might be 0. So if J is not susceptible, then this component size will be 0. So since S will not be in the word of mouth network. So this is x to the power of 0, it's just 1, times the probability that this node J is not susceptible, so not in the word of mouth network. And that happens with this probability. Okay, so this is probability of not being in the word of mouth network. Right? Plus here. Now we're doing okay, so S delta is, what's that? 1 plus this random variable. 1 plus this random variable. So we want to do probability generating function of 1 plus a random variable, then you multiply the probability generating function of the random variable times x. So you have this x. So now this should be the probability generating function of divided by expected degree. And here, since for J to be in a word of mouth network, J has to be susceptible. So then we have to multiply that by QD. So this is the probability that J has D friends and is susceptible. So that's this. But if J has D friends, excluding the original link, there are D minus 1 remaining friends. So the number of, so the size of the remaining component size, the size of the remaining component J belongs to is the sum of the size of the remaining component that J's remaining friends belong to. So, but each of this random variable is the same as delta because you find K1 by randomly following the link. Okay, so this random variable, once you given D, so if we know how many friends J has, then say J has 3 remaining friends, then this random variable is just the sum of, it's just 3 times S delta. S delta is a random variable whose probability generating function is expressed as H1. So the probability generating function of 3 times a random variable is, so if it's 2 times a random variable, then the probability generating function of that 2 times a random variable is just the probability generating function of that random variable to the power of 2. So if you want to do probability generating function of 3 times some random variable, then it's just the original probability generating function to the power of 3. Okay, so this is H1 to the power of D minus 1 because J has remaining D minus 1 friends. Okay, but this part looks just like here, the F1. Because this is the probability that J has D friends times some number to the power of D minus 1. D is a random variable. Okay, and the random variable whose probability generating function we express as F1. Okay, so then it's just F1 of, so instead of, so we replace the X with H1 of X. So then you can generate H1, so there's a self-generation. Okay, now, once we know H1, we can find the probability generating function of the component size of I. So if I is not susceptible, that is the probability that I is not susceptible, then the component size will be 0. Okay, so that's x to the power of 0. Plus, now this is the random variable of 1 plus D times S delta. So to do the probability generating function of 1 plus a random variable, you multiply the probability generating function of that random variable by x. Now this is a probability generating function of D times S delta. So with this probability, PDQD, I has D friends and is susceptible. Okay, so then you sum up the remaining component size of each of I's friends. Then you get the probability generating function of that is, this is a probability generating function of S delta. Okay, take that to the power of 2. Okay, so then once you know H1, you know H0. one, this has to satisfy this equation. Okay, so if you plug in x equal to 1, this is the number. It has to solve this equation. Yeah, that's, so h1 of 1p has to equal to, this is some function with h1 of 1p inside. Alright, so that's how you solve h1 of 1p. And what does that mean? h1 of 1p is the probability you plug in 1, then it's the probability that J is not in the word of mouth network because it's not susceptible, plus this is a probability that the remaining component size that J belongs to is finite because we're summing it up from 1 through all finite numbers. So H1 of 1p is the probability that J belongs to a small component. So the remaining component that J belongs to is small. So if J must belong to, so with probability 1, J belongs to a small component, then there's no giant component because I has finite remaining friends. So if J belongs to a small component for sure, then I must for sure belong to a small component. So for a giant component to exist, H1 of 1p must be strictly less than 1. So existence of giant component is equivalent to finding a non-trivial fixed point to this function that is strictly smaller than 1. And we can draw this function, this as a function of u. So this is for some probability generating some random graph model. This is how you can draw the G1 function. So a non-trivial fixed point exists, and it's convex. This function is convex. So it will cross, and it's equal to, so 1 is always a true. Let's go back. Yeah, if u is equal to 1, then this is equal to 1. So 1 is always a fixed point. So what we need is for this function g to intersect the diagonal line at somewhere between 0 and 1. So that means we need the slope of this function at u equal to 1 to be strictly bigger than 1. Okay, so now this is related to price. So then from here we can find out the critical price. Okay, so now let's go back to the implication for the model, original model. Okay, so the first result is that if price and the random network is such that this curve is steeper than the diagonal line, has a slope bigger than 1 at 1. If that is the case, and also this is saying that if price is higher, then we're lowering the probability. F1 prime. So when we take first order derivative, that's the expected value. So the expected number of friends, expected number of friends of J what this second assumption is saying is that when price is higher, then the expected number of friends J has in the word of mouth network is going to go down. And this is, you would think that often this may be true. If price is higher, probability of being susceptible generally is lower. So then you're lowering the number of friends J has in the word of mouth network. Okay. But whether this is true depends on network structure and whether theta valuation is independent of number of friends. Okay, but suppose this is true. So by increasing price, you're reducing the number of friends a consumer has. When you find a consumer by randomly following the link. Okay, so and what does this say? This says, this is just saying that if price is 0, that's the lowest, so that means everyone buys. Everyone is susceptible. And so if everyone is susceptible, then you're just asking about the original friendship network. So the first assumption is saying that if you randomly find a consumer by following a link, you find a consumer by randomly following a link, what's the number of friends this consumer has? Excluding the link that you find him with. And this is saying that, well, if you find J by randomly following the link, in addition to the original link, J should have strictly more than one friend. Well, if that is the case, then if price is 0, then you have a giant component. Intuitively, when you find J by randomly picking a link, then in addition to that link, J has more than one friend. So through J, you can find more than one friend on average, and for every friend of that, you can find more than one friend. So then the number of people in this component is going to explode. Okay, so that is the assumption. So suppose that at price in the original friendship network, a consumer, if you're randomly following a link, that consumer would have more than one additional friend. And if you increase price, the additional friend that consumer has is going to be strictly decreasing. It's going to be lower. So if that is the case, then there exists a unique critical price that is strictly positive, such that a giant component exists in the word of mouth network if and only if price is lower than this critical price. And what is this critical price? This critical price is such that at this critical price, the expected number of friends J has is exactly equal to 1. So if price is above this level, then there's no giant component. The network, so you can only find finally many people by following these links. Okay, and then you can actually calculate. So we have here you would have expected value of D squared minus expected value of D. So this you kind of have seen already. Okay, so first is existence of critical price, and then then what you want is to find the demand function, the fraction of consumers in the giant component. So H1 of 1 is the probability a consumer at one end of a randomly chosen friendship belongs to a small component. So it's a probability that this consumer is not informed by a word of mouth. So the probability a consumer with, so what we want to know is what's the demand? The probability a consumer with D friends is informed with what probability? So what we're asking is, we know the probability that J is informed. Yeah? So probability that J is informed is 1 minus H1. 1P. So H1 and 1P is the probability that J is not informed. When is I informed? I is informed as long as at least one of I's friends is informed. So probability that I is not informed is a probability that none of I's friends is informed. So the probability that I is informed is 1 minus the probability that none of I's friends is informed. So if I has D, this is the probability that I has D friends. This is the probability that none of I's friends is informed. You sum that over all possible number of friends I has. So this is the probability that I is informed. Okay. Now, what percentage? So if I is informed, then I will consider buyer. Now if we assume, we assume valuation and number of friends are independent. So that means QK of P. So for any degree, probability a consumer with that many friends is the sample is just 1 minus P. So if that is the case, then no matter how many friends I has, the distribution of valuation is just uniform between 0 and 1. So I will want to buy with probability 1 minus P, independent of the number of friends he has. So the demand function is just 1 minus P, so there should be a parenthesis. 1 minus P, that's the probability an informed consumer has valuation above price, times the probability a randomly chosen consumer is informed. And notice that 1 minus P it's a fully informed demand. If everyone knows the existence of the product, then the demand is 1 minus P. But because people don't know, people learns about it via word of mouth network, there's another term in the demand function, which is a probability a randomly chosen consumer is informed. It's
1 minus P.
There's a parenthesis. Okay, so then you can answer, once you have the demand function, then it's a standard monopolist problem. It's just that we need to look at the property of this function, the probability that I's friend is not informed. So given the assumption that valuation is independent of number of friends, then demand is more elastic under word of mouth than under floor information. And the reason is when you increase price, you lower the fully informed demand, but you also lower the probability a randomly chosen consumer is informed. But, all right. Okay, so demand is, given the independence assumption, demand is more elastic under word of mouth than under floor information. So suppose marginal cost is less than 1, then the monopoly price under word of mouth is lower than that under floor information. So monopolists will charge a lower price in order to incentivize people to share, and that would make more people informed about the product. But this conclusion may not hold without assuming the independence of valuation of number of friends, because without this independence, if you clustering, they look at connectivity. So here's one result of relationship between monopoly price and connectivity. So they have to assume that the distribution of friendship is described by a Poisson distribution with average number of friendship. So that's expected degree equal to z. That is, for z has to be greater than 1 for giant component to exist. And then, yeah, we need marginal cost to be smaller than 1 over z. And we also assume that the consumer's valuation is independent of number of friends. So it's the original assumption plus that distribution of friendship is described by Poisson, is a Poisson random network. Then the optimal price charged by the monopolist is increasing in the expected number of friends. So expected number of friends measures connectivity. This result is saying that monopoly price, optimal monopoly price is increasing in connectivity. But this may not be true outside Poisson random networks. Okay, so so I won't prove these results. So these, I see once they set up, derive the demand function, then the rest is to play with how like network structure affects H1. But I see this as like, you can use this as tool if you want to think about other kinds